Today we are going to discuss a very important integral theorem, and this theorem is known as Stokes theorem. Actually, Stokes theorem aims to convert or reduce the line integral of a vector function into the surface integral, and you can also convert the surface integral into a line integral by the use of this theorem. So in such problems, this theorem finds so much applications, and in this regard, this theorem is very important for you. So first of all, we will know what is this Stokes theorem, and then we will prove it. As an statement, you can say that if S be an open surface bounded by a closed curve C, and F be any vector field or any vector point function having continuous first order partial derivative, then this relation holds. That is, integral of f dot dr along a closed curve C is equal to integral over the surface S of curl f dot ds, or you can also write it equivalently, integral over S curl f dot n hat ds, because you know that this n hat is a unit normal vector at any point of the surface S, drawn in the sense in which a right-handed screw advance when rotated in the sense of description of the curve C. In fact, in other words, you can also say, as you know, this integral f dot dr along the closed curve C is nothing. This is simply the tangential line integral of the vector function f, or in other words, you can say this is just the circulation of the vector function f along the closed curve C. And this tangential line integral of vector function f along the closed curve C is equal to the normal surface integral of curl of f over the surface S. Actually, this closed curve C bounds the open surface S here. So this is the statement of Stokes theorem. In fact, to prove this theorem, first of all, we will change the mathematical form of this theorem, and then we will prove it. So let us see what is the alternative mathematical form of this Stokes theorem. As you know, n hat is a unit normal vector. So let us consider that this n hat vector makes an angle alpha, beta and gamma with x-axis, y-axis and z-axis. Let us say this is x-axis, this is y-axis and this is your z-axis. And we consider that this n hat makes an angle alpha with x-axis, an angle beta with y-axis and angle gamma with z-axis. Then you know cos alpha, cos beta and cos gamma will be the direction cosine of this unit vector n hat. In this condition, we can express the unit normal vector n hat in terms of these direction cosines. As you know, n hat will be then written as cos alpha I plus cos beta j plus cos gamma k. And R is the position vector of a point in a space, and if you consider that the position coordinates or space coordinate of that very point are x, y, z, then R is expressed as xi plus yj plus zk. And so this dr will be equal to dxi plus dyj plus dzk, since I, j and k are constant unit vectors. Now, as in the statement you can see there exists a curl of f. So first of all, let us find what will be curl of f. From the definition of curl of a vector, you know we can express this curl of f in determinant form in this way: curl f equal to this determinant which you can see here. And from this determinant you can express curl of f in this manner. When you will take I, then del fz by del y minus del fy by del z I plus, actually in second term of determinant there is minus sign, but I have taken here plus, so the order of operation will be just interchange. So when you will write plus, then you should write del fx by del z minus del fz by del x j, and plus now the third term k, that will be del fy by del x minus del fx by del y k. So this is curl f in terms of the normal in terms of the rectangular components of vector f. Now we will find what will be curl f dot n hat, because you can see in the mathematical statement of this theorem there is curl f dot n hat. So let us first of all find what will be curl f dot n hat. Since you can see curl f is equal to this much and n hat is equal to this much, so when you will take the scalar product of curl f and n hat, then only the similar term will remain and all the dissimilar term will vanish, as it takes place in case of the scalar product of two vectors. So you can easily see this product will be a first term del fz minus del fz by del y minus del fy by del z into cos alpha. Similarly, del fx by del z minus del fz by del x into cos beta, and del fy by del x minus del fx by del y into cos gamma, you can see, which we have written here. Now we also need to find f dot dr, because in LHS of the mathematical statement there exists f dot dr. Since f can be expressed as fxi plus fyj plus fzk and dr is equal to this much, as you have seen just now, so the scalar product of this you can easily see, this will be fx dx plus fy dy plus fz dz. So now after getting the value of curl f dot n hat and f dot r dr, you can express a Stokes theorem in this manner. Instead of f dot dr, we will write fx dx plus fy dy plus fz dz, as you have seen here, and instead of curl f dot n hat, you can write this expression which you have just calculated. So this is an alternative form of a Stokes theorem. So when we will prove it, we will prove this result, because this result has been obtained from the original statement of Stokes theorem. Now let us see how we can prove this result. For this, let us consider there is a surface S, as you can see in this figure, and this surface S is an open surface and it is bounded by a closed curve C, as you can see in this figure. This is the closed curve which bounds the open surface S. And actually this surface S we can define that Z equal to a function phi of xy. This is actually the equation of this surface S. So Z equal to phi of xy is the equation of S. And you can see I have shown in this figure that the projection of this surface S in xy plane is in fact this region R. So R is what? R is the projection of S in xy plane. And if R is the projection of surface S in xy plane, then the projection of this closed curve C in xy plane will be this closed curve C prime, which actually bounds this region R. So what is this C prime? C prime is the projection of C in xy plane. xy plane. Now we have to prove this result, as you can see here, which I have mentioned in this equation 1. So first of all, I would try to like the evaluation of the LHS, and for evaluating the term in LHS, first of all we will evaluate the integral of fx dx along the closed curve C. And when you will find the value of integral along C of fx dx, then on the basis of induction, seeing that result, you can easily say what will be the integral of the second term fy dy and the third term fz dz. So let us find what will be the integral of fx dx along the closed curve C. So you can say now integral along the closed curve C of fx with respect to x. Fx, you can say this is a function of x, y and z. What will be this? Since you have seen that the projection of this closed curve C in xy plane is C prime, so we can express this integral in this manner. This is integral along C prime fx of x, y, phi dx. Because you can see, since this C prime lies in xy plane and z is equal to phi of xy, so instead of z you can write phi here. Now let us simplify the RHS of this equation. You can write it integral along C prime fx of x, y, phi dx, and plus, since there is no term containing dy, so you can write this expression as 0 plus 0 dy. It will not make any difference in our result. So we have added 0 dy. Now you can compare this integral. This is just like I am writing it inside a bracket. You have seen in case of Green's theorem in a plane that m integral along a closed curve C m dx plus n dy. You have just seen this theorem in the previous lecture. What is this? You know this is equal to integral over the region R in xy plane and del n by del x minus del m by del y dx dy. This is nothing, this is simply Green's theorem in a plane, you have seen. So you can compare this result with the Green's theorem. In fact, at the place of m you can see there is in fact fx, and at the place of n there is 0. So using this Green's theorem here, you can write that this integral along C fx of x, y, z dx will be what? You can see this will be in fact del n by del x, and since n is 0, so the first term will be 0. So this will be integral over r, and first term will be 0 since n in this expression is equal to 0. and minus del y m, but at the place of m you can see there is fx of this much. So we will write fx of x y phi and dx dy. Since first term is 0, so you can write it in this manner. This is minus integral over r del y fx of x y phi dx dy. So by the use of Green's theorem, you have expressed this line integral along the closed curve C in this manner. Now let us simplify this RHS to some extent. Since fx is a function of three variables x, y and z, so we will simplify it by taking the partial derivative. So you can say see that this is minus integral over r. First of all, this fx will be differentiated with respect to x. So this is del fx by del x. But since finally we have to differentiate with respect to y, so we will write del x by del y and plus. Now the second term, this will be del fx by del y. Now I am differentiating it with respect to the second variable y and del y by del y and plus the third term will be del fx by del z and del z by del y. But since z is equal to phi, so you can write it del phi by del y and dx dy. Since x and y are independent variables, so you can see here when you will differentiate this x with respect to y partially, but x is independent of y, so this del x by del y will be equal to 0. So this first term actually vanishes, this will be 0. So you can write this relation, this result in this way: integral along C fx of x y z dx equal to what? You can see this will be minus integral over r. Now see the result here. First term is 0 and here del y by del y will be 1. So the second term will be simply del fx by del y and the third term will remain at it. You can see this third term. So what will be our result? This will be del fx by del y and third term remains same. So this is del fx by del z times del phi by del y dx dy, and say this is your equation number 2. Now you can see, to evaluate this integral defined in LHS of this equation, we need to find actually the value of del phi by del y and the value of this dx dy. So now our aim is to evaluate what will be del phi by del y and dx times dy in terms of s. For this, we will use the concept of direction cosine and the direction ratio. I hope you have studied this direction cosine and direction ratio in your course on vector algebra. So first of all, we will define the direction ratio of the unit normal vector n hat, which is actually normal to the surface S, whose equation is z equal to phi of xy. So you can see easily now the direction ratios of the normal n hat to the surface z equal to phi of xy are. What will be this direction ratio? In fact, the direction ratio of this unit normal vector, which is normal to this surface z equal to this much, according to this definition, you can say this direction ratio will be equal to, first of all, del phi by del x, del phi by del y, and this will be minus del phi by del z. Why minus? You can see, since the direction ratio, when you take the partial derivative of the function phi with respect to the respective coordinates, since in this case we find the direction ratio for z direction, and that direction ratio will be taken with negative sign, because in this case the n hat will have a projection in negative direction in case of direction ratio. So this is minus del phi by del z. But since phi is equal to z, so this will be minus del z by del z, and that is equal to minus 1. So these are actually the direction ratios of the normal unit normal vector n hat to the surface z equal to phi of xy. Now you know the ratio of the direction cosines and the respective direction ratio are constant. So you can see here that the direction cosine for the x direction is cos alpha, and the direction ratio for x direction is del phi by del x. So the ratio of cos alpha and del phi by del x, similarly the ratio of cos beta and del phi by del y, ratio of cos gamma and del phi by del z, that will be actually equal to constant, or constant means all those ratios will be same. So you can say, therefore, cos alpha by del phi by del x, this will be equal to cos beta by del phi by del y, and that is equal to cos gamma by minus 1. Now we have to find the value of this del phi by del y. So from these two relation, you can easily find what will be del phi by del y in terms of cos beta and cos gamma. So this result implies that del phi by del y is equal to, you can see here, minus cos beta by cos gamma, cos beta by cos gamma. So this is the value of this del phi by del y in terms of the direction cosines cos beta and cos gamma. Now you can see I have taken an elementary surface whose area is ds in this figure, and the projection of this ds on xy plane is this rectangle whose length and breadth are dy and dx. So you can say that this dx and dy is nothing. This is simply the projection of ds in xy plane. But you know the this projection has the area vector along the z-axis because it lies in xy plane. Since whenever a surface will be in xy plane and the surface is plane, its area vector is along z-axis. So you can say the area dx dy will be simply equal to the projection of this area vector ds in z direction. And can you say, since you can see this figure, this is the direction of area vector ds, and so its component in z direction, that is along this k hat vector, will be what? This projection you can write dsz, and this dsz will be equal to ds dot k hat, ds dot k hat. And since this ds dot k hat, this will be equal to what? This will be ds into mod of k hat into cos gamma, because this ds is along n hat and this angle is equal to gamma. This is equal to gamma. So this is simply equal to ds into cos gamma. And this dsz is what? This is simply equal to dx into dy, because the projection of this ds in xy plane is dx dy, and I have taken the projection of ds along z-axis, and projection along z-axis means projection in xy plane, because on xy plane z-axis is normal and area vector is always in the direction of the outward going normal to the surface. So you can say, since dx into dy is the projection, of ds on the xy plane, therefore dx into dy will be equal to, you have just seen what will be this. This is equal to ds cos gamma. So this is equal to cos gamma times ds. So you can see we have obtained the value of dx into dy here, and also the value of del f by del y. So these values of del f by del y from here, and the value of dx into dy, which is equal to cos gamma ds, we will now substitute in this equation 2 at the place of del f by del y and dx times dy. So see this equation 2, and I am just writing this equation after substituting the values of del f by del y and that of dx dy. So therefore you can say, from equation 2 we have, after making this substitution, you can see what will be the result. Integral along C fx of x, y, z dx. This is LHS of your equation 2 as you have seen. And this will be equal to minus integral over r. But since now we are changing the variable dx dy into ds, so instead of r, now we will write here s. And What is the first term? The first term is del f by del y. So write here del fx by del y. And the second term is this much, but when we will substitute this value of del f by del y, which is minus cos beta by cos gamma, so the second term will become negative. This is minus del fx by del z times cos beta by cos gamma, and outside of the square bracket there is dx dy, but dx dy is equal to this much, so you can write cos gamma ds. Now let us simplify a little bit of this RHS. You can see this is minus integral over s del fx by del y cos gamma. I am multiplying by this factor cos gamma to the inside terms, and minus, when we will multiply it in the second term, cos gamma will cancel out, and so this will be del fx by del z into cos beta. Cos gamma has been cancelled, and this is ds. When you will introduce this minus sign inside the bracket, then sign will be just interchanged. So this is integral over s and del fx by del z cos beta minus del fx by del y cos gamma ds, and say this is equation 3. So you can see we have obtained the value of this integral of fx with respect to x along the closed curve C. In fact, in similar manner, you can evaluate the value of integral of fy with respect to y along the closed curve C, and the integral of fz with respect to z along the closed curve C. Simply seeing this result which is defined in this equation 3, you can easily write what will be those integrals. So by induction, I am just now writing all those results. So you can say similarly, you can write integral along C. Now we will write fy here of x, y, z, dz, and this will be integral over s and del fy by del x. As you can see here, when we find the integral of fx, then always in the partial derivative there is a partial derivative of fx with respect to z and y, not with respect to x. Similarly, when you will find fy, integral of fy, then the partial derivative of fy will be here, and that will be actually with respect to the variables x and z, not with respect to y. So, and you can also see the direction cosines are cos beta and cos gamma. It means these are direction cosines for the y and z direction, not x direction. So whenever you will use this idea in the second term, then you will find that the direction cosines will be not of the direction of y, but that will be of the direction of x and z. So seeing all these things, you can write the expression for this integral. So this will be del fy by del x cos gamma and minus del fy by del z cos alpha. ds. Say this is equation number 4, and integral of fz of x, y, z, dz. This will be integral over s. Now here we should write the partial derivative of fz with respect to x and y, not with respect to z. Remember it. So this will be del fz by del y times cos alpha. Direction cosines will be in the direction of x and y, not in the direction of z in this term, and minus del fz by del x into cos beta ds. Now simply add all these three results, that is the results defined in equation 3, 4 and 5. We will simply add it, and after adding the results you will see that you will obtain the equation which I have mentioned here in this equation 1, which is actually the alternative mathematical form of the Stokes theorem. So let us add these results. You can see adding equations 3, 4 and 5, we get, what will be this integral? See the terms in LHS. When you will add the terms in LHS, that will be simply equal to fx integral along c fx dx plus fy dy plus fz dz. I have not mentioned these arguments here, and when the terms in RHS will be added, see here, this will be integral over s. Since ds is present in all these three equations, so take ds as a common factor and add the terms inside the square bracket. So you can see what will be your result. This is del fx by del z cos beta, del fx by del z cos beta, and minus del fx by del y cos gamma, and plus, now we will add these terms. This will be plus del fy by del x cos gamma minus del fy by del z cos alpha, and plus, now add these terms, del fz by del y cos alpha, and minus del fz by del x cos beta, and ds. Now see, del fx by del z cos beta, and in first term and in last term cos beta is a common factor. So we will actually select all those terms where a common factor is present. So this first term and the last term will be combined. Similarly, here is cos gamma, and here is also cos gamma. So we will combine these two terms again. And here is cos alpha and here is cos alpha. So combine these two terms again. So you can see what will be your result. After doing this simple algebra, you can see that integral along the closed curve C of fx dx plus fy dy plus fz dz, and this will be equal to integral over s. Now see, in first term we will first of all take this cos alpha as a common factor. So this will be del fz by del y minus del fy by del z cos alpha. So you can see this is del fz by del y minus del fy by del z cos alpha, and plus now take the cos beta as a common factor, and you can see cos beta is present in first and last term, so this will be del fx by del z minus del fz by del x. So this is del fx by del z minus del fz by del x, and plus now we will take the cos gamma as a common factor and select the terms. This will be in fact del fy by del x minus del fx by del y. So this is del fy by del x and minus del fx by del y and ds. Now you can see this result is nothing. This is simply the alternative mathematical form of your Stokes theorem. See here, I have written it in this equation. So you can see I have just proved the mathematical form of the Stokes theorem here, and so in this way you can easily prove Stokes theorem. In fact, as I have told you earlier, that this theorem will be just proved and stated in this lecture, but in the forthcoming lecture we will see its application. We will solve some of the important numerical problems which is very important for your competitive examinations and also university examinations.